Hello, everyone, and welcome to the first ever See the Change USA webinar. My name is Vincent Weiss. I'm the Manager of Product and Training Development with See the Change, and today we are going to dive into the first of three different series looking at Newton's Laws 1, and today we're going to be talking about momentum. So before we dive in, I want to just cover a few housekeeping items. So for this webinar, there will be no audio and you will have no video. So if you happen to turn your video on, just go ahead and shut it off. We will not need it. But since there will be no audio, we need to communicate. So we're going to use the chat box feature. If on your screen, if you don't see a chat box, put your cursor to the very top of the screen and a pop-down menu will come down, and there's a little ellipse on the far right side of that pop-down menu. Click on that, and then there's a little tab that says chat, and that'll open up your chat box. And I could just send a quick chat. So now I just sent a quick chat to everyone, and we can use this to communicate. So if you have any questions while I'm going through this webinar, do feel free to ask any questions and throw them into that chat box, and we will kind of discuss those. And at the very end of the session, we'll have a question and answer session where we can kind of take a look at those questions in detail. Also, this webinar is being recorded, so if you want to access this webinar afterwards and kind of go through some of the things that we kind of covered tonight, you can go through it and watch it again as many times as you'd like. And the PowerPoint that we'll be showing you tonight will also be available. And both of these two things, the recording and the PowerPoint, will be available on the Physics Lab, and it will be available on the See the Change USA Edmodo group. And I will show you how to access that group at the very end of this session. Okay, so the purpose of tonight is twofold. So first is to help you think like a physicist. So some of the concepts that we're going to be covering concerning momentum are so fundamental to physics that we see them again and again and again. We're going to see them in momentum, and we're going to see a lot of the same concepts in Newton's laws and also in the conservation of energy. So conservation of momentum, conservation of energy, Newton's laws with vectors. So a lot of these concepts correlate. So the sooner we can expose the students to these concepts, the more successful they're going to be when they see these things, when they look at Newton's laws, and when they see these things, when they look at the conservation of energy. And also, these topics are so real fundamental that just being able to understand momentum from a physicist's point of view will help you see motion in a completely new light. And also it is to help you build your confidence in physics. Perhaps you are nervous about physics and don't know a whole lot about physics. Well, I will tell you that if you can understand half of the things that I'm going to show you tonight, then you will be more prepared than perhaps 90% of middle school teachers teaching science. So if you could just understand half of it, you will be much, much more prepared entering into these topics when talk with your students. All right, so who is this for? This is for teachers looking to take their students to a deeper level of understanding. And it's also for teachers who do not have an extensive background in physics, but you would like to master the concepts. Or perhaps you're a teacher looking for alternate ways to explain concepts to your students. So if this describes any one of you, then you are in the right place. So real quick, what we are going to cover, we're going to cover the content found in lessons 1.3.1 through 1.3.4. So these are the first 4 lessons of Newton's Laws 1, and they specifically look at the topic of momentum. We're also going to talk a little bit about vector mathematics, and we're going to look extensively at the conservation of momentum and what this means. So after all of that, we're going to have a question and answer session about the content found in Newton's laws, specifically the first 4 lessons of Newton's Laws 1. And without any further ado, let us jump in. Okay, so imagine you have a hammer and that hammer has a mass. If this hammer was moving with a specific velocity, then this hammer would have what is called momentum. Momentum is defined by motional fortitude. So the hammer is going to continue to move until something stops it, and hopefully it's the nail. Momentum is given in physics, momentum is characterized by this letter P with this little arrow on top. The reason it's given P is because M was already taken to describe mass. So the next best letter, I guess, was P. So momentum, now I want you to notice this little arrow on top. This means that momentum is a vector. Now a vector can be represented by this arrow. And an arrow has a specific length and a specific direction. The length of this arrow represents the magnitude of the momentum, and the direction just represents the direction of the momentum. So when I say the length of the vector, what I really mean is this product defined by this equation right here. So P is equal to the mass of an object times its velocity. And this gives us the length of that vector. So this equation defines really what momentum is. So let's take a look at this in a very simple problem. Imagine you have a baseball and it's moving with some velocity, let's say 67 miles per hour, which is roughly 30 meters per second. And let's say that baseball has a mass of 0.14 kilograms. If the baseball starts moving, we can calculate the momentum of the ball by multiplying its mass times its velocity. And that gives us this number right here. So I want to point your attention to this unit, kilogram meters per second. So when we look at this unit, it's hard to get kind of a feel for what it means. But really what these units are used for, a kilogram meter per second is like a fingerprint that identifies momentum. As we start seeing more and more quantities like force and energy and power, they all come with these crazy sets of units. And all of these units are fingerprints for what they describe. So whenever we see some number followed by a kilogram meter per second, we know that this number describes the momentum of an object. All right? So the momentum equation tells us that momentum, mass, and velocity are all related. And here, let me try to represent how these quantities are related. So let's say that something is moving at a constant velocity. So imagine a big train that's moving at a constant velocity, and we're going to vary the mass. So imagine people are jumping onto that train as it's moving. What is going to happen to the momentum? Well, as the mass grows, as people jump on that train, the momentum grows. And as they jump off, the momentum decreases. Now what happens if we hold the mass constant? So let's say we have the same train, but this time we're not allowing passengers to jump on and off while the train moves. And we just speed the train up and slow it down. Well, the same thing happens. The faster it gets, the more momentum the train gets, and the slower it goes, the less momentum. The interesting thing happens when we kind of hold momentum constant. So there are several cases where two objects will have the exact same momentum, but they will move differently. And this is the reason why. So I want you to pay attention. What happens when the mass of an object increases? And what happens to its velocity? So as the mass of an object increases, its velocity decreases. And as the mass decreases, its velocity spikes up. So this is the only way momentum can stay constant. And what we'll see is if someone were to take a rifle and shoot a bullet out of the rifle, the bullet will have momentum moving in one direction, and the gun will have momentum moving in the opposite direction. And as it turns out, those two things will have the same momentum. But it's clear to see they do not have the same velocity. And this is the reason why. The more massive an object gets, the slower it goes. The less massive it is, the faster it goes. So up to this point, all we have really done is really defined what momentum is and defined what its relation is to mass and velocity. But we've not really talked really about any physics. Physics happens when we look at the transfers of momentum. So here's a hammer, and once it crashes down onto that nail, it transfers some of that momentum into the nail. And this is really where our focus is going to be. So all transfers of momentum must behave this conservation law, the conservation of momentum. And pretty much this law says that during a transfer of momentum, the total momentum before and after the transfer must remain the same. So there's one key term I want to focus your attention, and that is total momentum. A lot of times we're looking at situations where a lot of things are moving at the same time. And by total momentum, I mean the momentum of all the moving pieces involved. So when we're dealing with multiple moving pieces, we're dealing with vectors. So before we get any further, we need to talk a little bit about vector mathematics. So imagine you have these two vectors. And now imagine that these vectors represent the momentum of two different objects. Let's say they're two different billiard balls. One billiard ball is moving with this momentum, going this direction, and another billiard ball is moving with this momentum. So if we ask the question, if we have these two billiard balls just rolling, and we want to know what the total momentum is, we need to add these vectors together. So how do we add vectors together? Well, it's very simple. We follow two steps. The first step is align the vectors head to tail. Every vector comes with its own head and its own tail. So by aligning it head to tail, we set the tail of one vector on the head of the other. And it doesn't matter in what order we place these, because we're going to get the same thing no matter what. The second thing is we build a resultant vector. So whenever we align vectors head to tail, there's always going to be a dangling head and then a dangling tail. When we build a resultant vector, we connect an arrow from the tail to the head. So that would be given by this little red vector here. So this vector would represent the momentum of both of those billiard balls. So it's actually pretty neat how one single vector can represent the motion of two things at the same time. And in fact, we can extend this to talk about the motion of many things. So here we have four different vectors, and perhaps these vectors are all pieces of a ship that was floating in space and blew apart into four different chunks, and every chunk on that ship is represented by these different momentum vectors. And we're interested in the question, what is the total momentum of all those little pieces that are blowing apart? To add all of these vectors together, we follow the same two rules. We align all of these vectors head to tail, just like this. And there's a number of ways we can align them head to tail. And as it turns out, it doesn't matter which way we take, so long as we get the tails on each of those vectors touching the heads of other vectors. And now there's always a dangling tail and a dangling head, and we connect the tail to the head. And that would give us this little red vector here. So this vector represents the momentum of all those flying pieces that were just flying off in space. So we could say all those pieces, they go in different directions, but as a result, they're all moving pretty much in this direction with this amount of momentum. So we can actually say this is the momentum of that ship or that piece of rock or whatever before it blew apart. It's just kind of interesting. But let us move on and use some of these tools that we've just been talking. Yeah, I guess everything that I've been talking about so far has been dealing with two dimensions. Students, for the most part, in the middle school, 6th, 7th, and 8th grade, will be focusing on things in one dimension. So that has to do with vectors that either point in the same or opposite directions. So let us take this situation, two vectors that are pointing in opposite directions, and let's add them together to see what we get. We do the same thing, align them head to tail, and here is the dangling tail, here's the dangling head, and we build a vector right in here. So notice, if we wanted to know what the length of this vector is, we would take the long vector and subtract the short vector, and our resultant vector will point in the direction of the longer vector. So whenever we're dealing with vectors that are either pointing towards each other or in the same direction or in opposite directions, it becomes an addition or a subtraction problem. Now in this case, imagine if this top vector got a little longer. Well, the resultant vector shrinks. And if it got a little longer, it shrinks. And if it's the exact same length as the bottom vector, it's impossible to build a resultant vector. And we call this the zero vector. It's a vector without any length. And this tells us that whenever you have two vectors pointing in opposite directions that are equal in length, they cancel each other out. So this is very important. We will kind of see examples of this. So let's use these tools to kind of talk about momentum. When I say momentum transfers, this kind of breaks into two different categories. The first category is what I'll call separations. So imagine you're floating out in space and you have with you a big heavy bowling ball, and you throw the bowling ball away from you. So you're separating yourself from the bowling ball. Well, as you push off the bowling ball kind of pushes off of you, and you'll both be moving in opposite directions. So another example of separation is when a gun shoots, the bullet separates from the barrel. So these are what I mean by separations. And the next, we will take a look at our collisions. We won't go too heavily into collisions, but we'll introduce some of the main vocabulary. So starting with separations. Here is a cannon. Inside that cannon is a cannonball. So if we want to know the total momentum, we're asking the momentum of the cannon and the cannonball inside. And immediately we know that the momentum is zero. And how do we know that? Because the velocity of everything is zero. The velocity of the cannon and the velocity of the cannonball, they're both zero. Now, after it shoots, we know according to the conservation of momentum that the total momentum before and after must remain the same. So before it was zero, this means that somehow after it also has to be zero. And when I mean total momentum, again, I mean the momentum of the ball and the cannon. So the momentum of just the ball is not going to be zero, and the momentum of just the cannon isn't going to be zero, but the total momentum must be zero. So the momentum of the ball is pointing this direction, and the momentum of the cannon is going to be pointing in the opposite direction. So this is called recoil. If you recall from some of these old World War I films, seeing cannons being shot out, you'll see the cannon move in the opposite direction after that cannon blasts off. And what this equation pretty much tells us is that when we add these two vectors together, they have to give us zero. So we just saw that the only way for that to happen is if they are equal in length but opposite in direction. So the momentum of the cannonball, or of the cannon, is equal and opposite to the momentum of the cannonball. So if we take a look at just a little gun shooting some pellets, this is what's so interesting, is that the momentum of the gun shooting back is equal to the momentum of the bullets moving forward. And we just say, if that was the case, why doesn't it blow off your shoulder if you shoot a rifle? And the reason is because momentum is not the same as velocity. Remember, when you have two things with the same momentum, their velocity is dependent on the mass. And the gun is more massive, so that means it's going to move slower than the little bullets. See that in this nice little cute picture. All right, so let's take a look at another example. Rocket launches are a consequence of the conservation of momentum. So here we have two situations. So before the launch, we notice that nothing is moving. And whenever nothing is moving, the momentum has to be zero. So zero before the launch. This means that according to the conservation of momentum, momentum must be zero after the launch. And again, by momentum, I don't mean momentum of the rocket, but the total momentum of everything involved. So if we were to take a look at this scenario and look at all the momentum of all these gas particles being shot out, and combine that with the momentum of the rocket moving up, if we were to add all of these vectors together, we will see that they will all add together to give us the 0 vector. So as we see, after the launch, the total momentum is 0. So this obeys the conservation of momentum. Explosions are a consequence of the conservation of momentum. So this is really interesting. So take a look at these situations. You have these fireworks, and if we ignore these little sparkling ends, these two fireworks, they're not moving, so nothing's moving. So we can say the momentum is 0. And strangely, by the conservation of momentum, all of these particles need to give a total momentum of 0. So let's kind of see how this works. So imagine we were to kind of take all the particles moving in this direction, right along this black arrow. And we would say this arrow represents a momentum of all the particles moving in this direction. And I'm going to add these vectors up over on the left side of the screen. And here we have a vector representing all the particles moving up, and I've aligned them head to tail here. And these represent those particles. And slowly we go around looking at all of the momentum in all the different directions. Notice how after we align all these vectors head to tail, the very last vector touches the tail of the first. So basically, we cannot build a resultant vector. So it means that all these vectors add up to give us the 0 vector. So the total momentum of all these particles, after we add them all up, will give us a total momentum of 0. It's quite fascinating because even though they're blowing off in all different directions, they still give us a total momentum of 0. So it obeys the conservation of momentum. So now what about walking? This is a very interesting topic. So here you have a man who's just standing there. He's not moving, so his momentum is 0. And then according to the conservation of momentum, his momentum must be 0, or the total momentum must be 0 after he starts walking. So if the man is moving with a momentum going this way, the question is, what moves in the other direction? So looking at this, one may say, well, it's his legs. So as he walks, his legs move backwards. But what you need to understand is this momentum vector represents the momentum of every piece of his body added together. So this is including the motion of his legs, even if they're going backwards. So the only way to cancel this out, something else be moving in the opposite direction. As it turns out, this thing moving in the opposite direction is the Earth itself. And if this is the first time you've heard it, then you are probably thinking what this guy is thinking. What? How can it be? I can't believe this. Well, let's try to see how this can be. So if we look at the momentum of the man, his momentum is equal to his mass times his velocity. And the momentum of the Earth is going to equal the mass of the Earth times the velocity of the Earth. So if these two vectors are equal and opposite, then if we forget about direction, we can take these two values and set them equal to each other. Now what I want to do is I want to figure out how, if the man moves forward, how fast must the Earth move backwards? So I want to solve this equation for the velocity of the Earth. And I can easily do that by dividing both sides by the mass of the Earth, just like this. So here I have an equation that will tell me the velocity of the Earth. So let's kind of plug in some numbers right here. So an average man has a mass about 80 kilograms. And suppose he's walking at a swift 4 meters per second. This is a very quick walk. And the mass of the Earth is given by 5.97 times 10 to the 24 kilograms. So if we were to plug these three numbers into this expression right here, we will calculate the velocity of the Earth to be this incredibly tiny number. So to get an idea of how slow this is, at this speed, the Earth will move 1 centimeter in about 6 trillion years. So basically, this number is so slow that even our most sophisticated equipment could not measure it, which is amazing. It means walking has no measurable effect on the motion of the Earth. And what is so neat about it is that even though we can't measure it, we can still calculate how fast the Earth must move in the opposite direction. It's actually pretty neat, just from one conservation law. So it's a good thing too, because walking obeys the conservation of momentum. So that about does it for separations. So now we're going to get into collisions, and we're not going to go too deeply because the mathematics and collisions can get a little complicated, but we're just going to kind of go through this topic on a very intuitive level, and we're going to ask, how is momentum conserved? So when it comes to collisions, there's a whole spectrum of different types of collisions, but on one end of the spectrum, there are what we call non-elastic collisions. So these are things that when they collide, they stick together. And when they stick together, they lose energy in the form of heat. And then on the opposite end of the spectrum are elastic collisions. So during these type of collisions, things tend to bounce off of each other. And if it's perfectly elastic, no energy is lost at all. In fact, if it's completely perfectly elastic, there won't even be any sound because no energy is lost. But it bounces off. But the important thing is that no matter where we are on the spectrum, momentum is always conserved. And this is what makes momentum so useful when we're dealing with collisions, because a lot of the common physics tools dealing with Newton's laws and trying to use Newton's equations, or trying to look at the energy of objects when they collide, they're just not as easy to deal with because we don't have a fundamental conserved quantity that we get to start with. But the beautiful thing is that no matter what type of collision, momentum is always conserved. So it should be the number one tool we go to when we look at collisions. So give you an example of an elastic collision. Imagine you have this large truck and it crashes into this small car and they stick together. So if we were to just kind of take a look and measure the speed and mass of that truck, after it hits the car, it slows down because it transfers some of its momentum to the smaller car. And that net result is slowing down. Some common elastic collisions. If a nail is being driven into a piece of wood, a hammer will transfer momentum into the nail, and that nail transfers momentum into the wood in a very inelastic collision. And the wood transfers momentum into the earth. And car crashes are highly inelastic collisions. And one characteristic trait is that lots of heat is generated during inelastic collisions. So if you were to hammer a piece of nail into a wood and then turn it around and take it out and feel the nail will be very warm to the touch. And also, cars are designed to be highly inelastic because when a car collides with another car, you don't want that kinetic energy being transferred to the person inside the car. You want it being transferred as heat so that less of that energy affects the motion of the person's body. So the more inelastic the car collision, the better. Let's take a look at an elastic collision. So this is when things bounce off each other. If this red ball gets a little bit of momentum and collides with the blue ball, notice it lost all of its momentum and transferred into the blue ball. If we could somehow measure the momentum of the red ball before and measure the momentum of the blue ball after, we would see that they would have the exact same momentum. And also, if this was perfectly inelastic, no energy would be lost. So we can see the kinetic energy of both objects, and we would find that the kinetic energy of the red ball would be exactly the same as the kinetic energy of the blue ball after the collision. So, that's just what I just said. Here are some popular examples of very elastic collisions. So the Newton's cradle upper left-hand corner, and the game of pool with billiard balls are very inelastic collisions. So as it turns out, if we want to look at real collisions, they lie somewhere on the spectrum. Perfectly elastic collisions where things collide and bounce off each other and don't even make a sound, they obviously don't exist, and neither do perfectly non-elastic collisions. But real collisions lie somewhere in the middle. But the most important thing, no matter where we are on the spectrum, is that momentum is always conserved. And again, it should be the #1 tool that we go to. All right, so that about wraps it up as far as concepts of momentum. So now what I want to do is I want to open it up for questions. To ask a question, you can go up to the very top screen and a drop-down menu comes down, and then on the very right there's a little ellipse with 3 dots. Click on it, and then you'll see a little chat icon. So if you open that up, then you will be able to ask any questions. So right now I just want to give a few minutes to anyone who has any questions that I can answer. Okay. Oh, all right. So someone asked, how do I implement some of this in my classroom? So that's an excellent question. As I said before, this PowerPoint will be made available to you on both the Physics Lab and the See the Change USA Edmodo group. So within this PowerPoint are some really neat animations and tools that you can actually take and use and plug in. And some of these scenarios would be really excellent topics to spark discussion and to talk about different ideas relating to the conservation of momentum. Also, there is tons of resources on the Physics Lab for these specific 4 lessons, 1.3.1 to 1.3.4, and all those resources are available to you. Within the conservation of momentum lesson, there's a lab called the Marshmallow Lab where students will build a catapult launching marshmallows, and then they will look at the conservation of momentum. If we take a look at just that catapult and say, is that a separation or a collision? Well, we see that the marshmallow separates from the catapult, so it's an example of a separation. And the neat thing about separations is that they start off with a 0 momentum. So this means that after that marshmallow is launched, if something moves one direction, something else has to move the opposite direction to cancel that momentum out. So I would highly encourage you to have your students look for this. Launch that marshmallow and say, what happens to the catapult? And if you put it on a different surface, if you put it on a real rough surface or a really smooth surface, can you see a difference? And to really use this idea, can you identify that the momentum that the marshmallow has momentum in one direction, the catapult has momentum in the opposite direction. So those are some ideas that you can implement some of this. Do we have any other questions? Let's see, to what extent should my students understand these concepts? All right, this is an excellent question, another really good question. So I think there are 2 things that you can easily take away from this PowerPoint that will be really helpful in a class. The first is the concept with the vectors. The vectors are an excellent visualization tool to help diversify learning. So some students just can understand the concepts, but other students may need to see those visual representation of the momentum as those little arrows. And to use some of these vectors in the classroom will be a great way to just diversify the learning and add a little, just differentiate the instruction just a little more. Also, one of the biggest questions that students are always asking is, if I have an object and drop it, it hits the floor and the momentum of that object is gone and I can't see where it goes. Well, this has a lot to do with how massive the Earth is. So earlier in the slides, we calculated how quickly the Earth would have to move in one direction if someone else was walking in the other direction. And I would encourage you to show your students this mathematics and to show how incredibly tiny the Earth moves. And that will really help you deal with these concepts of how does the Earth play a role in momentum, because it plays a absolutely huge role. If we were to grow up in outer space, our idea of momentum would probably come a lot easier than if we grew up on the Earth, because even though we move and walk on the Earth, we never get to see the Earth move. It's because the Earth is so huge and it's so massive. Any momentum we take from the Earth or any momentum we apply to the Earth results in a very tiny velocity. And just showing them those little calculations and showing them how tiny that number is and how insignificant the Earth moves would be a really, really great way to talk about some of these difficult things with the motion between a body and the Earth. All right, can you give me a real-world example of how to engage my students in a concept of momentum? Yeah, absolutely. Let's see. I think if I was starting off teaching these concepts to students, one of the first things I would do is pose a hypothetical question and have the students kind of debate and think about this question and maybe have two sides to these two different answers. And this would be my question. So suppose you were on the football field and you were about to be creamed by someone. And that person was one of two people. You can either be creamed, tackled by someone who is really large but moving very slow, or you can be creamed by someone who is super fast but really small. Which person would you rather be hit by? So that would be the debatable question. So would you rather be hit by the really large, slow person or the really fast, small person? So that's how I would open it up, and I would pose that question and allow them to debate. And the beauty of that question is that immediately it gets them thinking about both mass and velocity, which is at the heart of momentum. Good question. Good question. All right. Okay, so I think I'll move on. Excellent questions. So next time we are going to be talking about Newton's 3 laws of motion. So we're not going to meet next Thursday because it's Thanksgiving, but in the following Thursday, December 3rd, I'm going to have another session at the exact same time. So, and as always, if you can make it, great. If you cannot, the session will be recorded. So to access the recording to tonight's session or to access the PowerPoint, both of these two things will be posted in the physics lab, but it's also going to be posted in the See the Change USA Edmodo group. So let me show you real quick how to access it there. So I'm going to share my desktop. All right, so here I am on the physics lab. And if you click on this little button, resources, there's a button for links. And then right here is a link that takes you to the request page for the Edmodo account. And if you're not familiar with Edmodo, Edmodo is a really, really awesome collaboration tool. And there'll also be some resources for you to find. So if you click on this little link right here, it'll take you to the Edmodo join request page. If you are not yet a member of Edmodo, you can easily create a free account. And all it takes is an email and a password, and you can create your own account. And then click on this link and send a join request. I'm already joined, so I don't need to join a request. But after you're in, clicking on the See the Change USA group, And here's the page right here. So as I said, it is an awesome collaboration tool. And after today, if you want to keep the conversation going and to spring up ideas on how you can introduce these concepts about momentum, it would be an excellent place to type this. All of the teachers that are on it, it's just a place for you to really keep the conversation going with momentum. But as I said before, right here, there's a subgroup, Unit 1.3 Newton's Laws 1, clicking here, and then clicking on this Folders tab right here. And as you see, there's a bunch of neat little resources. So under these resources, you'll find the video for tonight's session, and you'll also find the PowerPoint that was used during this presentation. So I would highly, highly encourage you, if you have not already joined the group, to join the group, and you'll be able to collaborate with many different teachers and talk about different ideas and different things that other teachers are doing, and it'll be a really, really neat place. So I highly, highly encourage that. So that's where you can access these two things. And as always, if you have any questions, any comments, concerns, feel free to either email me at vincent.weiss@seethechangeusa.org, or you can email Laura, which you all know. She's wonderful. You can email her at laura.horvath@seethechangeusa.org, or you can give us a call at 719-602-4440. All right, and if there are no other questions, I just want to thank you all for joining us, and we are very excited to meet with you again 2 weeks from today to kind of cover Newton's 3 laws of motion. And if there are no other questions, have a wonderful night, and we will see you all later.